So discrete Fourier series. Now, as I explained in the last video, that discrete Fourier series basically is going to come from this equation. So keep this equation in mind. How do we calculate discrete Fourier series? The concept is very simple. You take an analog periodic signal and you you get the samples out of it. So when you, of course, the original analog signal is periodic, and when you take the samples out of it at a sampling frequency, whatever sampling frequency is there, of course, your discrete signal is also going to be periodic. So when you have a periodic discrete signal, that means you can apply Fourier series on that. Remember, Fourier series is applied only on periodic signals, and of course it tells you what is the average value and fundamental component and harmonics. So now your signal is discrete, but it is periodic. Your sampling time is Ts. Your time period of the signal is still T0, because of course if the T0 was the original time period of the analog signal, when you take the samples, the time period is not going to change, it's still going to be T0. Sampling frequency, of course, is Fs, so it's going to look something like this. Right? So original periodic signal is in the dotted line, and then you are taking n samples in one time period. So T0 time period is n times Ts. Ts is basically the sampling time, right? So the Ts is the time between the two consecutive samples. That's the Ts. So the first sample, of course, it has become digital signal or discrete signal. So first sample is x0. The second is x1, x2, x3, x4, x5, x6, x7. So right now I have 8 samples total in one time period. Make sure you don't include this sample in the period, because the next period is starting from here. So that will be part of the next period. So I have samples x0 to x7. I have total 8 samples in one period over here, right? So if you know the sampling time, and if you know how many samples are in one period, you can easily find out what is the time period of the signal, right, through this equation or through this relationship, n times Ts. So now what we are going to do, we are going to take, and let me rewrite that, we are going to take our dn, what we had from exponential Fourier series. Dn was or is 1 over T0 integral from t is equal to 0 to T0, or one cycle, whichever cycle you are choosing, doesn't really matter, x of t e to the power negative j 2 pi f naught, which is omega naught, n t dt, right? So this was dn from right here, 1 over T0 integral from 0 to T0 xt e to the power negative j n omega naught t. Omega naught is 2 pi f naught, of course. So if we, and these are the components, remember these are the components in the spectrum, in the Fourier, in the on the frequency scale, these are the components of the signal, the spectral components of the signal. So if we convert this thing, remember this is for the analog signal, if we convert this thing into discrete domain, what we are going to get, T0 is n times Ts, right? All right, dt, we're gonna do dt as the time between the two consecutive samples, which is what, Ts. So dt is simply Ts, right? dt is Ts, right here, dt is Ts. And of course omega naught is 2 pi f naught, and t is n times Ts, right? The analog time t is n times Ts, which is the sampling time. So the first sample, of course, the 0th sample is going to be when n is equal to 0, the first sample will be when n is equal to 1, and so on and so forth. So we go ahead and change those values and change the integration into summation, because integration if your signal is continuous and summation if your signal is discrete. So we convert T naught into NTS, we change integral into summation, and in one time period we have n components starting from 0 to n minus 1. So 0 to n minus 1, x of n instead of x of t. NTS, remember x of NTS, this is x of NTS, but we are dropping the TS and we just write x of n. So x of n is x of NTS, e to the power negative j 2 pi n, that remains same. F naught is 1 over T naught, right? F naught is the frequency, fundamental frequency, which is 1 over T naught, and T naught is NTS. So that's why you see in the denominator NTS right here. And then T of course is n times TS. So here's a little bit of difference. Observe, it is K is the harmonic, over here n is the harmonic, right? Since we use n for the sample number in discrete domain, so we change the variable for the harmonic from n to k, and we keep n for the sample number in the digital domain, right? So instead of dn, basically it's dk, and then n over here is k. Just the change of variable to not to confuse between the sample number in discrete domain and the harmonic number in discrete domain. So k is the harmonic number and n is the sample number. So here basically is k. So k stands, and then t is NTS. So we go ahead and replace t by NTS, which is right here. All right, and then of course dt is TS. So this TS is going to be cancelled out by this TS. This TS is going to be cancelled out by this TS. So you're going to get 1 over n summation from 0 to n minus 1 x of n e to the power negative j 2 pi k n over n. And this is the discrete Fourier series right here. Discrete Fourier series. Again, observe, it's a complex quantity. dn or dk is a complex quantity. That means it has a magnitude as well as a phase. So each component has a magnitude and each component has a phase. Now, what is the difference between this and the analog? There's a very fundamental difference, and the fundamental difference is that your d of n, or the analog fundamental analog periodic series from here, right here, it is an infinite series. It is an infinite series. So you have infinite number of harmonics in the frequency domain. On the other hand, observe that you don't have infinite number of harmonics in the digital domain. You have finite number of harmonic from 0 to n minus 1, right? What does that mean? So dk goes from 0 to n minus 1, sorry, not n, but k is the harmonic. K goes from 0 to n minus 1, and we're gonna prove it. That means that you only need to know the frequency components for one cycle, and it is also periodic in nature, as you will see again shortly. It is periodic in nature. So not only your discrete signal is periodic in nature in the time domain, but the frequency components are also periodic in nature, and all you need to do is to find the frequency components, harmonics, fundamental, DC, over one cycle, and those components are going to be repeated over and over again. How we can prove that? The proof is right here. It is periodic in nature. So that means if we replace k by k plus n with the periodicity of n, and we replace wherever k is in this series, which is here only one time, we replace that k by k plus n, we expand this as you see, and then you distribute e to the power j2 pi k plus n into two exponential form, e to the power j2 pi k n over n and e to the power j2 pi cap n n. So this cap n will be cancelled out, and e to the power j2 pi n. What is e to the power j2 pi n? That was, hold on, this is the negative, yeah, that's a negative value, so it looks like it's positive, but that's a negative value. So both are negative values, remember. Anyways, what is e to the power negative j2 pi n? Remember, Euler's identity, cosine 2 pi n minus j sine 2 pi n. That will be e to the power negative j2 pi, sorry, this is n, lowercase n, not uppercase n. Okay, now remember, n is the harmonic number, 1, 2, 3, 4. So for any value of n, 2 pi times 1, 2 pi times 2, this is going to be multiple of 2 pi. What is cosine 2 pi n? It is 1. Cosine 0 is 1, cosine 2 pi is 1, cosine 6 pi is 1. What is sine 2 pi n? 0. Cosine 0 is 0, sine 2 pi is 0, sine 4 pi is 0. That means this component is 1. So you are going to go ahead and get the same expression for dk plus n as you have for dk. What does that mean? That means that the expression has a periodic nature. It has a periodicity with period of cap n. So you have n components, fundamentals and harmonic in one period, and that is going to be repeated in every period. So again, not only your input sequence is periodic, discrete, your spectrum, your Fourier series is also periodic and discrete, and this makes the discrete periodic series much different from the analog periodic series, because analog periodic sequence has infinite components, harmonics. This is I'm describing over here. Okay, so this is the fundamental relationship, that it has periodicity, right? The other relationship is that dk and d negative k are complex conjugate of each other. So dk is equal to d of magnitude of dk is equal to magnitude of d of negative k, and angle of dk is equal to negative of angle of d negative k. So when they are complex conjugate of each other, their magnitudes for the positive and negative values of k have the same value, and their phase for positive values are opposite than the phase of negative values. So they have periodicity, they have even symmetry for the magnitudes, odd symmetry for the phase, that is dk and d negative k are complex conjugate of each other. Okay, so when you plot dk in the frequency spectrum, remember k is kf naught, right? We're showing it k, but k is k times f naught. Now total f, and this is called frequency resolution. When you're plotting d, like we plotted c, when you're plotting d, let's say d of k, magnitude of that, then you have d of 0, d of 1, which will be the same as d of negative 1, same magnitude, d of 2, which is the same as d of negative 2, right? So and this is on the frequency domain. In the k domain, and then on the frequency domain, you multiply the value of k by f naught, because remember, the first one is what? The first one is at 0, k is equal to 0, you have the DC component. At k is equal to 1, you have the fundamental component, so this is f naught. At k is equal to 2, you have the second harmonic, 2f naught. So to go from the scale of k or axis of k to axis of f, all you have to do is to multiply k by f naught, and you will have the plot against the frequency scale. So f naught is a fundamental frequency, and it is called frequency resolution. In general, frequency resolution is basically the distance between the two consecutive components in the frequency scale. So this is, and it's expressed by delta f. So delta f is calculated as fs over n, because in one cycle the length of the frequency for one cycle is sampling time, sampling frequency, sorry, right? And why we are saying that? Let's relate it with the time domain signal. Let's go back this signal, right? T naught is NTS. Now remember, T naught is reciprocal of 1 over F naught, fundamental frequency. TS is the reciprocal of 1 over Fs, right? So when you have T naught is equal to NTS, T naught is 1 over F naught, and TS is 1 over Fs. So from this relationship you can see that Fs is equal to N times F naught. So in the frequency domain, one period is equal to Fs, and that is equal to N times F naught, right? So frequency resolution, which is F naught, which we give by we express by delta F, basically it is Fs over N. Frequency resolution is Fs over N. Frequency resolution represent the how small the frequency scale is in the frequency domain. So the smaller the scale, you will be able to see the components in a better way. You will not miss any frequency component if the scale is very small. It's not going to introduce any new frequency in the signal, but it's just going to fine tune the resolution of the frequency in the frequency scale. So you will see better what frequency components are included in the signal if your frequency resolution is sharp, that is small. If the frequency resolution is large, it's possible you may miss some of the frequency components that are part of that signal. So delta F is the frequency resolution. All right. This picture is going to show you what we were discussing. So the first component, the DC component, this is the plot of dk right here, magnitude of dk. This is the DC component, that's the fundamental component, as you can read from here, first harmonic. This is your kf naught. Well, first harmonic means fundamental component, of course, and then the second harmonic with the frequency 2f naught. Then you have the third harmonic with the frequency 3f naught. Remember, first harmonic kf naught is the fundamental component with the frequency of f naught. As you can see, it has the periodicity of n, and then it will start repeating itself, and it has even symmetry. So positive values at fk is equal to 1 will be the same as k is equal to -1, or f is equal to f naught will be the same as f is equal to -f naught, and so on and so forth. Now, when you calculate this, you will also see that you only have to calculate the values, basically, the values are only unique from 0 to n by 2, cap n by 2, or 0 to fs by 2, like folding frequency. Remember, fs by 2 is the folding frequency. So all the frequency components you can calculate from 0 to fs by 2. You don't have to go all the way from 0 to fs or 0 to n minus, or 0 to n, or 0 to n minus 1, sorry. So whatever components are between 0 and fs by 2, from fs by 2 to fs is going to be the mirror image of these components. So if you know these components, you can always produce a mirror image, and you can calculate the components over one complete cycle. But all you need to do basically is to calculate components, frequency components, from 0 to the folding frequency, or up to n by 2, cap n by 2, that is. But in general, we will be calculating components from 0 all the way up to fs, all of the components. And when you use MATLAB to calculate the discrete Fourier transform, it also gives you component the same number of points as the time domain signal. So remember, k goes from 0 to n minus 1, as well as lowercase n in time domain goes from 0 to n minus 1. So both have the same periodicity, and that's a big difference between, again, the components in the discrete domain and the components in the time domain for discrete.